Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about the logistic growth model, another model and application that can be used with differential equations, or that differential equations can be used to model a given scenario. Okay, all right, so let's get started and see what this model is about. So here's the simple concept behind the model. Suppose that I started a rumor, let's say in a school, all right? And I told one person that I was retiring at the end of the year. How long do you think it would take for everyone in the high school to know? Now, we have to take technology and throw it out. We can't use it. So you can't mass text, group text all your friends and tell them everything, in like 5 minutes. You have to tell the people the traditional old school way, which is one person at a time. All right. How long do you think it would take for everyone in the high school to know? And we're not going to spread this rumor outside the high school. It's only within the high school because only the people in the high school are actually going to care. All right. And what would that look like? So, I think the answer to, how long it would take everybody to know is, well, pretty quickly, right? I think pretty quickly people would be able to figure that out. Okay. But what would that model look like if I were going to graph that, right? What would it appear to be? So let's say that I graph time on the x-axis and the number of people who know the rumor on the y-axis. So let's say there's 1,000 people in the school. So you can't go above 1,000. All right, you can't go above 1,000. Okay, there's no reason to. All right, so we're starting with one person who knows it. So that's down here. One person knows it, and now they're going to spread the rumor. Now, how does it work? Right? Now, that one person, all they can do is tell somebody else, right? They can't can't text people or anything like that. They just have to literally go up and tell them. All right. So at first, the rumor would actually spread pretty slowly, right? Because there aren't a lot of people who know that I'm going to retire, right? There aren't a lot of people who know that I'm going to retire. So there's not a lot of people to tell the rumor, but there's a lot of people to tell it to. So it's going to start by growing pretty slowly. Okay. And then as time goes on, as more people know, well, when more people know, they'll be able to tell more people. And then at some point in the middle, right, there's going to be a lot of people knowing. Why? Because you have a lot of people to tell the rumor who know it, and a lot of people who still need to know it, right? So it's going to spread really rapidly in the middle, and then toward the end, it's going to, phase out, because at that point, there aren't a lot of people who need to know. There's a lot of people to tell it, but there are very few people who need to know once you get toward the end, so it's going to kind of flatten out at the bottom. All right. This model is called the logistic growth model. Okay. It's the logistic growth model. So I like to use this example because I think it's a great way in a school to explain the logistic growth model here. And this is how it works. All right. Truly. So at the beginning, not a lot of people know it, so not a lot of people can tell it. They got to tell it slowly. But then in the middle is where it really picks up, because you got a lot of people who still need to know, and then you're going to have a lot of people who can tell them. And then towards the end, it phases out because there aren't many people left to tell. Okay, so let's talk about this model mathematically. The logistic growth model, dPdt, the change in population with respect to time, is equal to K times P times the quantity A minus P. So here are some characteristics of the logistic growth model. The limit as t goes to infinity of P of t is equal to A. All right. A is called the carrying capacity. So in our example just a moment ago, the carrying capacity was 1,000. You're not going to go beyond 1,000 people you're not going to tell more than 1,000. All right. They use this model a lot in biology or environmental science. So if you're talking about ecosystems, and let's say the one population gets above 1,000, gets above the carrying capacity, then once you're above the carrying capacity, then the population or the ecosystem tries to force the population back down towards 1,000. So if you get above the carrying capacity, then you're going to the model forces this value back towards the carrying capacity. All right. Okay. dPdt is equal to 0 when P equals 0 and when P equals A, the carrying capacity. All right. And then there's a point of inflection at T equals A over 2. So that point of inflection is actually pretty important, and you can understand what it's there for. Here's that point of inflection, right, where the graph changes from concave up to concave down. So this on my graph is A over 2. So that you kind of understand what's happening. A over 2 is that point of inflection. It's the point where it changes over. So if I were to take 1,000 and divide by 2, that would be 500. So if we go back to our rumor example, when 500 people know the rumor, that's when the rumor is spreading the fastest, right? Because 500 people know it and 500 people still don't know it. So the rumor can spread very rapidly at this point. Okay. And then once you get beyond 500 people knowing the rumor, it starts to flatten out, because if you're one of the 750 people who know the rumor and you tell somebody else in the school, chances are whoever you tell probably already knows. All right, because there's only 250 people left who don't know at that point. Okay, so this point of inflection is actually very, very important. It's the point where the rumor spreads the fastest. All right? Because like I said, when 500 people know it, 500 people don't know it. So if literally all 500 people who know it happen to tell 500 people on the first time who don't know it, well then literally the number that do know it is going to jump up really, really quickly. Okay? So those are the characteristics. All right, so we're going to try one example with the logistic growth model here. So the growth rate of a population P of pandas is given by the differential equation dPdt is equal to 0.8 P, quantity 1 minus P over 100, where P is measured in years. Letter A wants to know what the carrying capacity for pandas is. So the actual differential equation should be dPdt equals Kp A minus P, right? Where A is the carrying capacity. So to do this, I would need to actually find a common denominator inside the parentheses here. So dPdt would be 0.8 P 100 minus P over 100. And then that would allow you to take the 100 out if you wanted to. And you could write it as 0.8 divided by 100, P 100 minus P. So the carrying capacity is that number there. It is 100. Letter B wants to know what is the panda population when dPdt has a maximum value. So when the rate is a max, I want to know when the rate is a max. The rate is a max at the point of inflection, right? That's when the rumor's spreading the fastest, at the point of inflection. The point of inflection is when P is equal to A over 2. So that's 100 divided by 2, that's 50. And then letter C wants to know what is the rate of change of the population when the population's growing the fastest. Well, the population's growing the fastest when P equals 50. What is the rate of change of the population? So what is dPdt when P is 50? Okay, well, I'm going to substitute it in. So dPdt would be, I could do it in many ways. We'll use the original, 0.8 times 50, 100, 1 minus 50 over 100. So that's 0.8 times 50 times 1 half, right? 50 over 100 is a half, 1 minus a half is a half. So let's see. Let's do 0.8 times 10. That would be 8 times 5. That's 40 times 1/2 would be 20. So PDT, the rate of change in the population, is 20 pandas per unit or per year. Okay, and that would be my answer to part C. And that's it. That's how the logistic growth model works. Okay, I think it's easiest to think about in terms of a rumor that's spreading around your school. And as always, thanks for clicking.